Good evening, everyone. Hope you all are doing well. So today, we're just going to finish up chapter 12. So I won't hold you all too long. Um, can you all hear me? Take that as a yes. All right, good deal. So, capacitors. Why are capacitors important for circuits? Why are they important? And I know you could read it, but I don't want you to read it, which I know you're going to read it, or you should have already have read it. But if you are familiar with capacitors, this is just, get your brain started. Why are capacitors important for circuits? Why are they important? What is a capacitor? Are you all familiar with capacitors? It's apart from the definition. Yes, they store energy. Absolutely, they store energy. Why are they important?
So that some of the memory isn't lost.
Oh, there's no energy. So some energy is not. So some memory isn't lost. That's what you're saying. So some of the memory from what isn't lost? Right. That's it. More or less, Sahil. And I think Lawson, I think you're on it. Sort of. If you read what Sahil is saying, what in that light, I wouldn't say memory, but if you think about a capacitor, it stores energy. So then, if there is a power surge and you lose power to, say, your computer or whatever your whatever circuit is being used, typically for a computer, more or less, when you think about a computer and you think about a power surge, um, what it does is it keeps the energy provided to whatever system you're using that has these capacitors. And yes, it's going to die, of course, your computer or what have you, if you don't have a battery in it. But the main function of the capacitor is to help store energy and then continue to provide energy to the system you're using, um, if there is a power surge, right? So what I like to compare capacitors to, I like to compare a capacitor to an accumulator when it comes to a mechanical system. The accumulator, um, you flow basically a fluid inside of it at or to a certain pressure, and then you'll run um, your system, your mechanical system, from the fluid flowing out of your accumulator. So you would basically charge the accumulator. Say your system has a maximum allowable working pressure of 2,000 pounds or 2,000 psi, pounds per square inch, right? And instead of running off directly from the source, you'll run off the accumulator because you'll get a constant flow of power from your fluid from your accumulator versus what is similar to a power surge. What we call it in the mechanical terminology is a pressure spike, right? Because the pressure spike is if you're wanting to maintain that certain pressure on your sorry, I'm trying to catch my wind here. In a mechanical system, if you're wanting to maintain the same pressure or constant pressure throughout the system, right? Versus coming directly from the source, because your source could be rated for 10,000 psi, right? And then you got to regulate that pressure, right, into your system if it's only rated for 2,000 psi. And but still, you can get a pressure spike from you regulating it, whether that is a hand regulator or a hand valve, right, or a ball valve. You can still get a pressure spike. And if you get a pressure spike, that could damage something downstream of your regulator or your relief valve or what have you. And so you'll put an accumulator in place to prevent that. All right. Now, if that made sense to you, that's the same use of a capacitor, right? It helps prevent pressure surges. I said pressure surges. It helps prevent power surges, right? So it mitigates that. So that's why you would have a capacitor in your circuit. All right. Now, if you don't know what a capacitor is, you can Google it, or I'm going to show you. I'm just basically going to share my screen. I don't think I have a picture of one in my slides. But no fear. This is what a capacitor is. That's a capacitor. And these are capacitors. And then an accumulator, for those of you that are curious, or those of you that don't know. This is an accumulator, a pressure accumulator. Well, more or less this guy, right? It's a DOT cylinder. DOT is just some pressure code, ASME code, to say that it's certified to hold a certain amount of pressure, more or less. But yeah, that's an accumulator. And it's interestingly enough how similar they look, right? But obviously they have different materials. So just a fun fact. So back to, again, the lecture at hand. Just regards to capacitors. What else do we need to know? Let's see. Obviously, you saw the units, so farad. And then the size of a farad, and all of the stuff that you could read is more or less, I would just study that from your book. But then let's go talk about some batteries. Batteries, it's like a secondary power, right? Or even your direct current. Batteries flow like a direct current. And I had a video. Let me see if I can pull it up. Pretty cool video. Talk about rechargeable batteries, how they work. I think this is it. No, that's not it. Let's go with this one. It's not exactly the one that I wanted to show, but we'll go with it. It's about 8 minutes long. So You know, every time when they say when you were in middle school and when your teacher was out, there was always a movie, and then she always wanted you to write up something. Well, maybe you guys didn't have this, but when I was in school, you have a, a, um, a substitute teacher. They'll show a movie, and then and if y'all were like me when I was in high school, movie time meant it's time to go to sleep. Now, I'm not saying that because it's time for you guys to go to sleep because it's all about that final. So I'm just saying you should take notes on this video because it's going to be sharing some information that will more than likely be on the test. All right. So let's run it. Wait, let me run it back. Stop sharing. I always forget to click share my audio whenever I do this. All right, let's go.
What's something you do every day? Eat, sleep, charge your phone, your laptop, your portable charger to charge your phone and laptop? Chances are, if you're watching this video, the process of connecting your assortment of electronic devices to a wall charger before you go to bed has become a mundane, daily routine. After all, the phrase, "I need to charge my," gives us over 600 million search results on Google. In a world where so many people are in dire need of charging their electronic devices, it seems only logical that we understand the process of how our reusable batteries are charged. But what exactly does this phrase mean? Are little bolts of lightning being transferred to the cores of our smartphones? Is there a container that gets filled with green juice once the battery is fully charged? Turns out, this concept of rechargeable batteries storing energy is a bit more complicated. Like in so many other topics in chemistry, my explanation will begin with atoms. Atoms are made of positively charged particles called protons, particles with no charge called neutrons, and negatively charged particles called electrons. Sound familiar? That's because when these electrons move through a circuit, we get electricity. But we'll come back to that later. Generally, because the number of protons and electrons in an atom are equal, the atom is neither positive nor negative. However, when an atom loses or gains an electron, the charge of the atom is no longer neutral. An atom with a net positive or negative electrical charge is called an ion. An important thing to note here is that atoms prefer not to be ions. That is, when they gain or lose an electron, they try their best to become neutral again by moving electrons or finding oppositely charged ions that also want to be neutral. Now, back to batteries. All batteries are made up of three major parts: a negative anode, a positive cathode, and the electrolyte. The chemical reactions that occur between these three parts of a battery are what causes electricity. Ions in the electrolyte react with atoms in the anode, resulting in a buildup of electrons. These unbalanced electrons cause the anode to be negative. In the cathode, the chemical reaction with ions from the electrolyte causes a lack of electrons, making it positive. Now, what we have here is too many electrons in the anode and not enough electrons in the cathode. Naturally, the electrons want to leave the anode and instead enter the cathode. To prevent electrons from traveling directly from the anode to cathode within the battery, the electrolyte acts as a barrier. Only when a circuit is closed, meaning a wire connects both ends of a battery, can electrons flow from the anode to cathode. The loss of electrons happening in the anode is called oxidation, while the gain of electrons happening in the cathode is called reduction. Combined, the transfer of electrons between two materials is called a redox reaction. And voila, electricity. The different types of batteries that have emerged throughout history are caused by the variation in metals and solutions that have been used as the anode, cathode, and electrolyte. Let's take the first battery ever created as an example. You've probably heard of the term volt, used today as our standard unit of electric potential. It comes from the name of an Italian scientist, Alessandro Volta, who, in 1799, created the first battery. His invention, now called the voltaic cell, consisted of layers of zinc, copper, and cloth soaked in a chemical solution. Even in the original battery, the zinc, as an anode, went through oxidation, while copper, as a cathode, went through reduction, causing the electrons to flow from negative to positive. Today, the most commonly seen batteries in households are called alkaline batteries. In alkaline batteries, the negative anode is zinc, the positive cathode is manganese dioxide, and the electrolyte is the basic potassium hydroxide. The problem with all the batteries we've talked about so far is that eventually the atoms in the anode run out of electrons to pass on to the cathode. When all of the metal of the anode is oxidized, the battery is considered dead. Fortunately, the development of these non-rechargeable batteries, or primary cells, has led to the invention of secondary cells, the type of rechargeable batteries used in our mobile phones and laptops. What makes secondary cells special is that this oxidation-reduction reaction process can be reversed. When these cells are connected to an outside energy source, the electrons in the cathode are forced to flow back in the opposite direction as in the discharge process. The electrons once again bond with the ions in the anode, allow the battery's charge to be restored. Most secondary cells on the market today are lithium-ion batteries. The combination of carbon as an anode and lithium cobalt oxide as a cathode allows electrons to be flowed back and forth through hundreds of charges and discharges. However, even rechargeable batteries eventually die. Over time, as the number of charge cycles increase, the repetition of the redox reaction causes chemical damage to the metals, lowering their capacity. The electrons lose a place to be stored inside the anode and therefore cannot flow to create electricity. Of course, the lifespan of rechargeable batteries varies by manufacturers, model, and treatment. Scientists continue to explore new options of materials to lengthen discharge and shorten charge times of secondary cell batteries. Regardless, this reusable alternative to non-rechargeable primary cell batteries has allowed our electronic devices today to be compact and practical, even if we do have to charge them more often than we'd like to.
Well, that was cute. All right, so I just wanted to share that just to give you a sense of how batteries work, then also how rechargeable batteries work. The other video, it was cool too, but it wasn't as cute as this one. But it just showed how the metal that is the barrier, and how you have the electrons trying to basically go across the barrier, but then when you connect the wire to it, it flows through the wire to connect attach itself to in the cathode and all of that. I know I'm not a big battery person, but that's why I let the video do the talking. But in the processes, I thought it was just super cool how when you connect it or when you put a battery in use, how all of the electrons flow out. And then when it came to the rechargeable battery, how when you basically put it in the same, almost but a reverse, when you're plugging in your phone into the wall and supplying power back to the battery, it then forces it back to go the opposite direction or in the reverse direction, which she didn't really go into explaining that. But this other video I had, which I couldn't find, they actually went into the explanation of how that process works. And using that metal barrier is actually what helps you reverse that role of how the electrons flow out. But don't worry, I won't test you on that. But it was really cool process to see, especially for you, those of you that are going to be doing electrical engineering. Nonetheless, I'll stick to the rivers and lakes that I'm used to. But anywho, batteries, back to batteries. As you know, batteries produce electricity from a chemical reaction. Just as she was explaining, when the device is on and the circuits create paths for electrons to flow through and create chemical reactions. When the device is off, there is no path for the electrons to flow. All right, simple stuff. But just like when resistors are in series, you also can have batteries in series. All right, and so batteries are placed in series arrangements to increase the voltage output. And I always ask students, names an application where you would have a battery in series, like something that you use in your household right now where you would have batteries in series. A remote. Remote control. I don't think I've ever seen a remote control with the batteries in series. Because my remotes, the batteries are parallel. Meaning they're side by side. But when the battery is in series, they're stacked. Flashlight, there you go, Z. Flashlights are typically, the batteries are typically in series. I've never seen a battery. I do have a flashlight where the batteries are in parallel, and that thing doesn't work very well. I actually got it through my job. It's an interesting little gadget because you could take out the compartment where you load the batteries, and then you can put it back into the flashlight. But typically, the batteries are in series, and when the batteries are in series, the output voltage increases. So if you have more than one batteries that are 1.5 volts, right? You'll add up all that. You'll add up each voltage output from each battery, and you'll get a total voltage, right? So if you remember, when resistors are in series, that's JoJo. He's barking at people that are coming across. Oh, never mind. My wife just got home. Thought he normally likes to bark at people when they're passing by our door. But anywho, so if you all recall, when a resistors are in series, it does not build up the output voltage, right? The output voltage remains the same. And actually, the current across each resistor totaled together is equal to the voltage that was the input voltage, if that makes sense. But here, when you stack batteries in series, you're increasing the voltage. So then what about when you have batteries in parallel? You're increasing the current. All right. So Batteries in parallel, increasing the current. Batteries in series, you're increasing the voltage. Any questions on that? All right. Good deal. So all the thing that I have, like the stuff that you can read, not really gonna go over this. Colors of light. No. No. Nope. Okay. Well, everything else is more or less just reading. So I'll leave all the reading to you guys. But if you do not have any questions in regards to the homework or your lab, hopefully your lab will make more sense. And just to go over the lab again, now that you have seen circuits work and all of the above. So what you're going to be doing, there are multiple circuits. And so I think if we give you various resistances or the quantity for each of these resistors, and you have the circuit, and what you will have to do, you'll solve for the current or in the voltage or what have you, and you will basically verify it through the simulator just to check yourself to see how this circuit would work, or see how the resistors would work within this circuit, or see how the current flows within this circuit, right? And then you will check yourself with the simulator, and you'll just report on how the current and resistors all work throughout the circuits, in a parallel circuit, in a series, in a circuit that is in series, and you will basically just run through the explanation on your report on if your work that you did through each circuit is feasible. Does it make sense that you may have the voltage drop across a resistor within a circuit that is in series, right? It just asking, basically, you're just doing a verification check. Does it make sense? Now, you're not going to just say, yes, it makes sense, right? You're going to expound upon why, and, from what you've learned about circuits, the reasoning behind it. All right. Any questions on the lab? I know we went over it last week, but just bringing it back up. Nope. I believe it's due Sunday. Can't remember. I believe it's due Sunday. Yeah, I believe it's due this Sunday, the lab report. So, yes, you have 4 days to complete your report. All right. And then your project is due, I believe, the 9th of May, your final project. So what happens is we have 2 more lectures, right? That's next Tuesday and next Thursday. After that, I'll have the lectures scheduled. But so if we were in person, you would just come to class to work on your final project. But seeing that we don't have class and everything is virtual, if you need to set up something with me, the week following next week, then you so that if you don't, then you don't have to show up for class. So let me just put some dates on what I'm talking about, referring to. So the 27th and 29th will be your last official lectures. but the 4th and the 6th, there will be no lectures. All right. And so if you guys have questions, or if you need help on something, just let me know. Just shoot me an email. And if y'all want to meet up during our class periods, then we can definitely do so. All right. And if not, then you don't have to worry about it. Yes, Cassandra P, we do have a final exam. And I want to say it's the 6th, but I can't remember. Let me look at the calendar. It's either 6th or the 13th. Let's see here. Yes, it's the 13th. Sorry. So your final exam is May 13th. All right. And I'll just open it up that day. Yes, May 13th. And I'll open it up on the 13th. And you'll have basically that day to complete it. And I think I have to have all the grades submitted by the following Monday. So what day is the following Monday? So I think I have to have everything submitted by May 17th, all of your grades submitted by May 17th. All right. Yes, the final project is a group project. Yes, I'll be close to my email. Thanks, Hunter. Yes, I'll be close to my email if it doesn't open. What I'll know more or less, I'm gonna, because there's no class, I'll just like come to my desk during your period and just turn on turn everything on, like my email and everything. So, but yeah, your final project is a group. Yeah, nah, it isn't. Because the last two, man, it's been horrible. Maybe I'll have this one open before the scheduled time. And then, y'all can just go in there and then y'all will be surprised, like, what? Finally, we get an exam that's actually open. Right? That will be cool. So you never know, Hunter. I might send that thing through next week. I'm not gonna do it next week. I'm just kidding. No, the final exam, because I have to have your grades in by the 17th. So yeah, I'm gonna make sure. I said this last time, I know, and it's recorded, that I said I wasn't gonna let it happen again. So rest assured, this time, okay, it's not gonna happen again. Okay, never. Well, I won't say never because it might not, but not for you guys. Maybe my next class. That's not funny. That's not funny. Oh man, but I'm so silly. But yeah. Don't worry, no worries. Y'all gonna be fine. Everything will be fine. So next week will be your last 2 lectures, and then the following week is just, hey, if you guys want to come in and work on your project, you need my help, I'll be available. I'll come in, I'll turn it on. Basically, I'll join the session. More than likely, if I'm the only one there for the first 30 minutes, I'll leave. So, but there's 30 minutes of lecture on the week of through the whatever that was. I think it was the 7th, May 4th through the 7th. Yeah, I'll come on that Tuesday and Thursday at 8:05, and I'll just stay on for about 30 minutes or so, and then I'll leave just to see if anybody comes in, if they had any questions or whatever, need help on something. So yeah, that's fine. I mean, if you needed something, you don't have to, Lawson, because if you don't need anything, there's no point in coming on. But if you need something, yeah, jump in and then we can discuss. So, but if there are no other questions, you're all free to go. We'll see you on Tuesday. Y'all have a great weekend. So Thank you. Have a great night. Thank you. Thank you. Have a great night. Have a great weekend, everyone.